So hello friends, welcome back to our channel. In this video we will be seeing how to interface EEPROM AT24C512 device with the STM32F103 C8 device, C8 controller. And yes, before starting to explain our code, I will just show you the glimpse of that our code is working. Many of the followers that are mentioning that our code is not working properly. So like we will build our code. Here you can say here you can see that we have built our code. Now we will go back to our controller setup. We have our device STM32F103 C8 and AT24C512 device. Then we have connected two pull-up resistors of 4.7k 4.7k, and we have connected one output LED D1 to pin PC13, and we are using GPIO as a I2C interface. We are not using the default I2C library for our project. And yes, we will load the hex file. We'll load the hex file. Now first thing you have to set is crystal frequency, that is of 8 megahertz, because in our setup while configuring the device it is mentioned that 8 megahertz crystal is externally connected, so that we have to do. Now as you can see, we have our EEPROM interface hex file, and today's date is 25th August. So 25th August and 3:25 p.m. 3:26 p.m. it is correct. So we will open it. We'll click on OK. Another major thing that we have to consider is go to the design tab, go to the configure power rails, then in the ground we have to make sure that we have ground, VSS and VSSA. The voltage is set to 0. Go to VCC VDD. The voltage is set to 5 volt. For simulation purpose we are setting the controller voltage to 5 volt, or else we can set it to 3.3 volt. VCC VDDA, all these three should be connected to VCC or VDD. And then we will go to VEE. We have to set this voltage to 0. By default it will be to -5. We have to set it to 0, and there will be no nets connected to VEE. Then we have to click it on OK, run. So currently there is no transaction on the I2C pins. As you can see, we have few data that is already there in our I2C EEPROM. We will run the simulation. The simulation is running. We have not connected any oscilloscope to monitor the I2C sequence, that is start, stop condition, how data is written, but I'll make sure that I'll explain it thoroughly. Once we can see few transaction on the clock and data pin of the I2C of the EEPROM device, then we will make sure what are the contents that are written on. We will check those contents. For I2C clock and data, we have used PA0 and PA1 of the STM32 controller. We have given the initial delay as large initial delay. Oh, I guess there is some issue. Interface dash ID. we have our code from initialization, everything written. I'll copy it and go over here, use your code to begin, paste it here, use your code to end, and Ctrl X. So yes, first thing that we are doing after our main code starts running is we are erasing the EEPROM. Then we are writing the data, that is this array data, character array data, into EEPROM with starting location at 0x00. Then we are reading from that same location 0x00 and we are writing it to A0. So we will change this data to 256. We'll change this data to 256. We'll save it, make it 0. Then we'll load the hex. So yes, as we can see, there is transaction on the clock pin and data pin. We'll check. As you can see, whatever data was here, it is getting erased. Now we will have to wait for the data string to get written. Till that time, let me walk you through the code or the basic configuration, or the basic pin configuration. Till that time, let me walk you through the basic pin configuration of the STM32. So we have set up PA0 and PA1 as GPIO output, PA13 as GPIO output, and PA9 and PA10 as UART pins. So we'll go to system core, RCC. First we will set the external high pass crystal as ceramic clock resonator. Then we will go to NVIC, we are not setting it up. PA0 low push pull, no pull up, GPIO output level as low. PA1 GPIO output level as low, output push pull mode, no pull up is required. And PC13 GPIO output level low, GPIO mode output push pull, internal pull up is connected, and maximum output low. So that's the GPIO configuration we have done. Now we are not setting any ADC pins for this project. We are not using any timers. Then we will go to connectivity, use ART1. The mode will be asynchronous, baud rate will be 9600, and that's it. We are not using the interrupt for this. Then we will go to clock configuration. As I mentioned that in the external clock, the external crystal clock frequency, that is of 8 megahertz, as we have said in the simulation. So this is 8 megahertz. We will be using the maximum clock frequency. So HSC, we will be using the PLL source, external source as a input to the PLL. Then 8 PLL multiplexer is set to 9. Then it will be going to as a PLL clock. For system clock, we will have to select it as PLL clock. Then 8 into 9 will be 72 megahertz will be our system clock. Then our prescalers then our peripherals won't be running at the maximum frequency, so we will be having the APB 1 prescaler as divided by 2, so 36 will be the APB peripherals. The maximum clock will be 72 megahertz to APB 2 peripherals and the APB 1 timer clocks. So currently PLL clock will give us 72 megahertz of clock. We will go to clear, generate the code. Yes, we'll check whether it is done or not. So till this time it is not completed. We'll go into our main code. Yes, so still our code is there. We'll close this code, close this project. Make sure that we are setting the GPIO pins as output port. We'll go through each of the functions once our simulation is completed, initial simulation is completed. After that, in the last, we will change the data so that we can demonstrate that the data is getting correctly written. It is not something that we can claim the simulation is not working properly. So we will change the data, and in the part 1 we will be seeing the erase functionality and the write functionality. So we can see we can write one byte of data and we can write multiple byte of data. So both functions we will check. We will make the changes in the code according to that, and I will tell you how to use those functions. And you can get those two libraries from my Telegram channel. You can get those two libraries, EEPROM.h and EEPROM.c files from my Telegram channel. So till this simulation gets done, we'll go into our code. We'll walk through our code. So here it will be main.h. We have to include EEPROM GPIO pin.h. So we have to use this hash include. This is system generated. Now you can add the arrays that you want to print. So this is currently unused. So in the main in our main code, we have declared one array. So that array is of uint8 type, data type. So this is a byte array. The variable name for this byte array is valdata. You can give any data type, and it is array of characters, so we have given like this. This is the standard syntax for defining the array. So we have currently 64 bytes of AA data, then BB, CC and DD. We'll change few of this data so I can demonstrate that it is correct. Then AB, C and D. So copy this, paste this, this. And we'll type 1 2 3 4. We'll keep the data as random, so in between I'll let the data as it is. and we'll keep it as it is. Now we have to get the size of this array, data character array. So we are using size of var data, and we have stored it in uint32 4 byte data variable var1. We have to give the pointer to this array, so we have used pointer, a byte pointer, that is. Then while reading back the data, we will be needing some memory. So we have created the array of 256 bytes. We have initialized it with null 0, that is 0, and we have provided one pointer to this read data array. Now these are all system generated. Now EEPROM initialization. For EEPROM initialization, we are using two pins like SDA pin and clock pin, right? So we have to set those pin as high. So whenever our program will run, at first it will be set to high, both the pins will be set to high. But why we have set the SDA pin as high first and clock pin as high first? Because like we know the start sequence and stop sequence of I2C protocol. So when clock is high and there is transaction on the data line, so it will be considered as start or stop condition. So we have to set the data pin first, and then we have to set the clock pin later. So after some delay, we are setting the clock pin. So this is EEPROM initialization function. Then we are giving some few delay, a delay of 1 second. Then EEPROM erase. Going into EEPROM erase, we are using 512 kilobits of data. So 512 kilobits, that is 1024. So 512 into 1024 divided by 8. So this will be number of bytes that we will be able to write this many number of data into the EEPROM. We'll check now. Okay. So as you can see, our data is correctly written. So yes, our data is correctly written into the EEPROM. Now we will stop this. We'll go again back to our code. So this will be the data size, that is 512 into 1024 divided by 8. This many number of bytes that we will be able to write in our EEPROM. Then we have used one flag, that bit start or stop condition. I'll explain the use of this flag. Now when we want to erase the EEPROM, whole EEPROM, we will be needing to erase these many number of bytes. So we have used uint32 value. We are using a for loop UI. Unless this variable is less than the data size, we will be incrementing it. Okay. So initial stop condition, start stop condition. When start stop condition flag is set to 0, we will be writing the start condition first. Then we will be setting this flag to 1. Then we will write the then we will write the device address with the right opcode, and we will set this to EEPROM I2C pins. Then we will write memory address, and then we will write the data. Now for these 512 kilobytes of EEPROM, the page size is of 128 bytes. So after 128 bytes, like we have to send the stop condition, or it will start writing the data from the 00 again, start of the page, same page. So we have to send a stop condition. Then again we have to send the next with the device address, we have to set the next memory address. So for this we are using a for loop. So basically stop condition, it will send start condition, it will send with this flag it will send a start condition. After 120, after it is like once it is set, right, once it is set, it will go into EEPROM data write. It will send the FF to each byte. So once sorry my bad. So it will send FF data, that is 0, like it is the erase data. So it will send FF data to FF data bytes to each of the memory address. So it will write FF to each FF byte to each memory address. Then we will check that if UI plus 1, that is this variable plus 1 modulo 128 is not equals to 0, sorry, is equals to 0, that is it is the last minus 1. It is what we can say, the memory address is at the sector end. So we will be checking this, the memory address is at sector end. So let's suppose if UI is at 127 plus 128, right? At memory address 127 we will be needing to send a stop condition. So 127 plus 8 divided by 128, we will get a reminder at 00. That's why it will send a stop condition, and it will set this flag, start stop condition flag, to 0, so that we can again send a start condition at the next memory address. Okay, so till that, from 00 to 127 bytes or 127 memory locations, we will be sending the FF data to each memory location. Okay, first we will check what is written into start condition, what is written into stop condition, and then we will go into EEPROM data write. Okay, now coming out of this loop, for loop, it will check that if this variable UI variable is less than the data size, or this coming out of this loop, to come out of this loop, it will need to check that UI is equals to data size. That means it has reached the data size, right? This variable UI variable has reached the data size. So it will come out of that loop. It will check whether this flag is set to 1 or 0. If it is set to 1, then it will again send a stop condition, clearing the write operation or whatever the operation we have started, right? In this case we have started the erase operation, so it will end that erase operation by sending a stop condition. Now we will go into start condition. First, before that, we will check start and stop conditions of EEPROM. These are the basics I2C start and stop conditions that we are following. So as you can see, a start condition, it is already mentioned, a high to low transaction from a high to low transaction of SDA, that is of SDA with SCL is high, SCL high. So when clock is high, transaction of data line from high to low indicates a start condition. Okay, stop condition is what is a stop condition? When clock is high, from low to high transaction on data line, it will be considered as a stop condition. So we will go to our code, start condition. What is our start condition? High to low on data line when clock is high, right? So we are making sure that our clock is high, then we are assuming that our SDA pin, data pin, is already high. So high to low transaction on data pin when clock is high, it is considered as a start condition. After that, we are bringing the clock pin to low. So as you can see, after this start condition is done, we have to bring the clock to low, right? One more thing, the transaction on the data pin will happen only at when clock is low. Okay, else it will be considered either a stop condition or start condition. So transaction on the data pin can happen only when clock is low, okay, for the data to send. Now we will go back here. So we are setting high to low on SDA when clock is high. We are making the clock high, high to low transaction on the SDA, and again we are making the clock as low, okay. And opposite to this, our stop condition, right? Low to high transaction on data line when clock is high, right? So making sure our data port SDA line is low, clock is high, right? SDA pin again we are setting to high. So low to high transaction on data line when clock is high, okay. So we are completing our start and stop conditions. I hope this is understandable. Now we will go to our data write, EEPROM data write. We are sending the device address. So here in the EEPROM.h, GPIO pin.h, you have to clearly mention this device address, whatever device address that you are setting. For my simulation purpose, I am setting the device address as A0 because I have connected A1 and A0 as 0, and in the datasheet you can see the device address as A0 basically. So I will show you that again. Device addressing, yes. So MSB is 1010.000. So it is 1010, that is A, and 000, right? So this is my device address I have set according, okay. Then for write opcode it is 0, read opcode it is 1, right? So you can see this, right? This bit, whenever we want to write a data, we have to set it as 0, this bit as 0, and whenever we want to read the data, we have to set this bit as 1. So 8 bit of the device address is the read write operation select bit. A read operation is initiated if this bit is high. So whenever this bit is high, that is 1, it is considered as a read operation, and whenever this bit is low, that is 0, this is considered as a write operation. So for write operation 0, read operation 1. Now clock port and data port, we are obviously using the GPIO ports, so we have to define those. So for clock port, GPIO A, for data port, GPIO A, for clock pin, GPIO pin 0, and data pin, GPIO pin 1. You can select according to your simulation, right? And then these are the these are the function declarations that we are using for our simulation, okay. So whenever we are writing the, okay, we will go to write operation. So when we want to write the data at particular memory address, we have to initiate a start condition, then give the device address, then send the first word address, then second word address. These are the memory locations that we want to write the data on. Then we have to send the data. This is for byte write, that is single byte write operation, okay. And whenever we want to send multiple bytes, right? So start condition, device address, read write operation, we have to select it. Then memory address, we have to whatever we can say, is we have to write a start of memory address, right? First memory address from where we want to write the data, okay. Then this will be the multiple data, and then stop condition. So whatever operation we are starting, we have to make it stop to complete the EEPROM read write erase operation, okay. Now we will go over here. We are sending the device address, then the memory address, okay. As mentioned in the datasheet, we are sending the device address and the memory address, and then we are sending the data. So we'll go device address A0, like 8-bit, okay. So 1 byte of data, uint 8 data byte. We are running the for loop for 8 times, okay. So whatever this data is, either the device address, memory address, or the data, right, that we want to send on the SDA pin of the I2C pins, right, SDA pins of the I2C protocol. Then we are taking this data, we are shifting it by 7 minus UI variable, this UI variable, okay. So for 0, we can see that data is shifted 7 times. So the MSB is will be brought to LSB. It is ANDed with 0x01 and it is written in the data bit. So we are sending the MSB first, okay, and LSB last. So we have set or reset the whatever the pin is, GPIO pin, right, SDA. We are sending the MSB first on the I2C data line. We are sending the MSB first on the I2C data line. Then we are giving the EEPROM clock. So in the EEPROM clock, we will go into EEPROM clock. EEPROM clock. Yes. So EEPROM clock, we will go into EEPROM clock. We are setting the clock pin, and then we are, after some delay, we are resetting the clock pin, okay. Then UI will be incremented to 1. So 7 minus 1, it will be 6, right, means bit number 6 will be so bit number 6 will be brought back to 0 or LSB. It is ANDed with 0x01 and the data bit is set or reset according to the bit number 6. So it is returned to the pin, and as you can see, we are already setting our clock as low. So at this moment the clock is low whenever the data transaction is happening on the data line, okay, low to high or high to low for the data. So again, after this we are giving the clock. Then again UI will be incremented to 2. The 5th bit will be brought back to LSB, send it over the SDA line of the I2C, give the clock. So according to this, we are sending the data, 8-bit data. Now first we have set the device address, send the device address. On the 9th clock cycle, we have the device will send the acknowledgement, okay. So it will, when the acknowledgement bit is set by the EEPROM device, it at that time it will be 0 at the level 0, okay, meaning that positive acknowledgement is received. So for EEPROM acknowledgement, we are writing this pin as low. We are giving 1 clock cycle delay. Then we are giving the clock set and reset, okay. After few seconds of delay, set and reset. Then go back to our main code. So this is clock pin. So this way we are writing the data to the EEPROM device. This is 1 byte of data. Now we are writing the first device address, then the memory location. Again, in the memory location, our memory location is of total 16 what we can say 16 bytes of memory location, or 4 byte of memory location, not 16 byte, sorry, our memory location is of 4 byte. So first yes, sorry, our memory location is of 2 byte, okay. So our memory location is of 2 byte. So we are sending the first byte here you can see 1 2 3 4 5 6 7 8 bits, that is 1 byte, 2 byte, right? First byte, then second byte, right? The MSB or higher byte is sent first, then the lower byte is sent. So UI is shifted 8 times, that it will bring the higher byte, higher 2 byte or higher byte to lower byte, sending it. Then we are ending with FF, that is we are only sending the lower byte. So if, to give a clear understanding, if our data is like ABCD, memory address is like ABCD, AB will be sent first, right? So AB will be brought back to lower byte, so AB will be sent first, and then CD will be second, CD will be sent, okay? So ABCD, whatever we can say this, okay? Once this is done, I guess we are not going to start stop condition. Yes, so yes, this is the erase operation. Likewise we will go to our write operation, EEPROM write. It is same, memory address, pointer data and data size, right? So start stop condition flag, right, to check at the sector and page sector boundary. To check the page sector boundary, we are using this flag to send the start stop condition. Then we are writing the device address with write opcode, because we are using the write operation. So device address, then the memory address, higher byte first, lower byte second. Then we are writing the data. Then we are again checking the page boundary, okay, using this. Then we are sending the stop condition. So let's suppose that we are not writing at the page last byte at the page boundary. So for that, what will happen is this condition will false, this condition will be false, so no stop condition will be sent at this point, okay? But UI will be equals to data size, so it will come out of the for loop. At that time our flag will be already set to 1, so flag is high. Then after coming out of the for loop, we will be sending a stop condition. So that's why we have written the if loop over here to complete the operation, okay? So let's save the code, and again for the verification purpose, we will write few data, that is FGHI. We will save the code, we will build the code, okay, and we will load the hex file. So current 404, okay, AT24C512. So initial contents of the memory, I have not loaded any of the memory files, okay, and then we are loading it. Yes, so as we can see, there is transaction on clock and data pins of the I2C. We'll pause it, we'll check all the memory contents are 00, sorry, all the memory contents are erased, that is set to FF. We are writing the data at 00 location. So in the code we can see we are writing the EEPROM data after erase operation, we are writing data at 00 location, okay? So let's continue to run our simulation or wait for our simulation to complete. So till now, if you like my explanation, just share my YouTube channel, just share my videos and click a like button. So if you like my videos till our simulation run, if you like my explanation on this topic, click on like, subscribe and share my video. Also let me know what topics you want the explanation on, or you want the simulation on. I will be making videos on to that. It took me a while to complete this simulation. It is not hard and fast, but I was not focused. So yes, it was a bit of a time, and after a long time I am uploading a video. Again, and on the few of the topics, a few of the followers said that my videos are not working, my code is not working. So I will be explaining those codes again. I will make sure that I am running those codes again on my laptop, and I will be recording all the modifications that I am doing, or all the changes that I am doing. I will be uploading those videos onto my YouTube channel, so you can follow those changes also. After erasing the EEPROM, we are writing the data at 00 location, and we are writing this complete data. I will be fast forwarding this section. One more feature of EEPROM is, so if the data is already present at particular memory location, we can directly overwrite that data without needing to erase the EEPROM. But it is always the best practice to erase particular data sector or page before writing the new data onto that page. Again, if you ask me why it is taking a long time to complete the simulation, so I will explain. We have checked the one attribute, that is the write cycle of the EEPROM needs to be waited for 10 milliseconds. So in our simulation it is 10 millisecond, and if we check the timings, it is where it will be the timing, select maximum timings will be somewhere, it will be the timings. So in the timings we can see that the wait we after we initialize or after we send the stop condition, right? Yes. So these are the AT characteristics. So after sending a stop condition, right, we have to wait for 5 milliseconds to complete that operation, and in our simulation it is already set to 10 milliseconds. So for the IC in the simulations it is 10 milliseconds. So I will show you in the stop condition. After we complete the stop condition, we are giving a delay of 10 milliseconds. So that's why to completely erase all those pages it is taking a long time. After writing the data at particular page, it is taking a delay of 10 milliseconds. So yes, that's the reason it is taking a long time to complete the simulation. But as you can see, our simulation is completed now. We will check the data. So here, as we have written in the code, FGHJ AB, so you can see that FGHJ AB, and this is 1 2 3 4 16. Then we can say 1 2 3 4 1 2 3 4 1 2 3 4, and we have written the particular data, right? So we are writing the data, complete data, at these locations and all these memory locations, and it is getting written correctly. Now again, to demonstrate, we will just comment out this, right? We will only write EE. These are total 64 bytes. Then we will write from EC0. So we will write the data from EC0. The read back functionality is not needed right now. EC0, we will write the data at EC0, and we will erase the EEPROM chip. (414) set to OK. As you can see, data is erased. Now we are writing EE at starting location will be EC0. So the simulation is complete. We will check the results. The EE should be 64 bytes of EE should be written at the memory location 1C0, that is correct. And as you can see, these are the 16 bytes, so 16 into 4 64, and at the end 00 is written, that is correctly written. So yes, our code works perfectly fine, as you can see. So thank you guys for watching my video. If you guys like my video, the explanation, please click on like, share the video with your friends, and thank you for watching.